Hello everyone, and welcome back to the series on single variable calculus. Today we're going to continue our exploration of functions and limits and look at one very important application of limits, and that's known as the continuity of functions. So let's suppose that some function f is defined on some domain, and let's denote that domain as DOMF. Let's choose a particular point in that domain, and let's call that point A. So suppose A belongs to the domain of f, then we will say that f is continuous at that point if for all epsilon greater than 0, typically epsilon is chosen to be arbitrarily small, but as long as it's positive, it's okay. Then there exists an associated delta also greater than 0 that is typically also going to be arbitrarily small, sometimes proportional to epsilon, such that if the distance between x and a is arbitrarily small, then the distance between f of x and f of a will also be arbitrarily small. Now, if you compare this to the definition or the formal definition of a limit, you may see some similarities between them. In particular, the only difference in these definitions is this element here, where this in the limit definition was actually the limit of the function. Remember that if a function is not defined at x is equal to a, the limit can still exist here. But since we're assuming that a does belong in the domain, that means f of a does belong to the range of that function, which means that the distance between f of x and f of a does exist, and hence we can mandate that distance to be arbitrarily small. So, what does that exactly mean? So as x gets close to a from all possible directions, that means the f of x values will approach this defined value of the function when x is equal to a, and its name is f of a. Now, some people will take this as a theorem or an alternative definition depending on the rigor behind the discussion. But we can equivalently say that f is continuous at that point if the limit equals the function value, and this theorem can be easily seen as a corollary from this definition because that's practically what's going on here. So how can we take this algebraic theorem, corollary, or alternative definition to sort of give us some graphical insight as to what the function is doing? So let's give an example of some function, and let's give it some interesting shape. Let's assume that our function has this particular pattern, right? So let's call this function f. Let's choose an arbitrary point a in its domain. So let's assume that this is our chosen a point. So since it belongs in our domain, that means there exists an associated point in the range that is associated to it. So that distance right there is going to be our f of a. So what is happening to the limit as x gets close to a from the left? Well, obviously, as we choose an arbitrarily small neighborhood around a, we can clearly see that the values on the left-hand side are going to get closer and closer to a. The values on the right-hand side are also getting closer and closer to a, obviously at different speeds, possibly different values. But nonetheless, as x gets close to a from both the left and the right, it is approaching the y value f of a, compared to the case where if our function value was defined down here, notice that it's going to approximate that y value instead of the actual f of value, which could be literally anywhere or not existent. But since we're assuming that a is in the domain, f of a has to exist and it has to be somewhere. All right, so with that being said, now we can sort of give a couple examples on what it means to not be continuous. And if we say if f is not continuous, then we say that the function is discontinuous. So discontinuous. And these are sometimes called points of discontinuity. So a few of the cases where a function would be discontinuous would be something along the following. So let's assume we have a curve, let's assume we have a hole, and let's assume that it sort of does its own thing outside of that point. And let's define that point to be something, but not at that hole. Notice that if that y value is equal to 5 and that y value is equal to 10, notice that the limit is equal to 5, but the function value is equal to 10. And since the function value and the limit value are not equal to each other, that means it's not continuous and hence discontinuous. But this discontinuity is very easy to fix or very easy to remove by simply taking that dot and filling in that hole with it, and therefore that discontinuity would then be removed. So this discontinuity type is often referred to as a removable discontinuity. Of course, removable discontinuities are not the only types of discontinuities. For example, you can have a closed circle there, you can have an open circle somewhere else, and it sort of does like this. Notice in this removable discontinuity world, and we can actually write down some of these theoretical observations. So we see that the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x. So that means that the limit exists, but we see that the limit as x approaches a from all directions is not equal to the function value. So from this definition, we say that f has a removable discontinuity at this point. But in this case, we have that the limit as x approaches a from the left does not equal to the limit as x approaches a from the right-hand side. But do note that the limit from the left does have some limit value, and they're both finite, but they're not equal to each other. So notice that the limits both exist and are finite. And this is often called a jump discontinuity, because it either jumps from bottom to top or jumps from top to bottom, depending on the directions on the left and the right-hand side. So another case of jump discontinuity, one could say, is one that sort of looks like this. So let's, for example, have a vertical asymptote at some number. Let's define our function on that vertical asymptote, and let's assume that it has, for example, it sort of approaches a finite value on the left-hand side, but it's asymptotic on the right-hand side. So it goes up to positive infinity from the right-hand side. So notice here that the limit as x approaches a from the left does not equal the limit as x approaches a from the right. Now it could approach positive infinity or negative infinity from both the left and the right, but for this type of discontinuity, which is often referred to as an infinite discontinuity, we just will classify as the limit as x approaches a from the left and the limit as x approaches a from the right. They could be equal to each other or not. That's not the point. Here, one or both are infinite. So one could say that an infinite discontinuity is sort of a special case or an extreme case of a jump discontinuity, because technically we're jumping from this finite value up to that infinite value, or jumping from that infinite value down to that finite value. So those are the three common types of discontinuities that you may encounter in your journey of functions. Now that we have some basic insight of what it means for a function to be continuous at a point, and some cases and graphical interpretations of what it means for a function to not be continuous, i.e. discontinuous at a point, let's look at an algebraic example and sort of see whether it is or is not continuous on its domain. So here let us assume that the domain of this function is chosen to be the set of real numbers. Obviously at our breakpoint for our piecewise function, 1 is included there. So the entire real line is accounted for. So the question then becomes, is it continuous at 1? Is it continuous everywhere else? So if you look at the graph of x squared plus 3x on its own, you should know that that is the graph of a parabola. And you should be able to graphically accept at the least that all parabolas are going to be everywhere continuous on their domain. And similarly for x minus 2, that's the graph of a line, and one should be able to at least graphically convince themselves that lines are also continuous everywhere on their domain. Moreover, one should be able to prove with some other theorems that every polynomial is continuous on their domain. As long as you're not introducing anything weird, it's usually well behaved. So, the left-hand side of this curve is continuous, the right-hand side of this curve is continuous, but what happens at the point where it switches from one polynomial to the next. So let's evaluate f of 1. So we know that this function is defined at 1 for the second piece, so this is just going to be equal to 4 times 1 minus 2, which is equal to 2. So, if this function truly is continuous at x is equal to 1, the left-hand limit and the right-hand limit both must be equal to 2 as x approaches 1. So let's test that to see what's going on there. So the limit as x approaches 1 from the left, and the limit as x approaches 1 from the right. So, as x approaches 1 from the left, that's going to be piece number 1. So that's going to be 1 squared plus 3 times 1, which is the same as 1 plus 3, which is equal to 4. And as x approaches 1 from the right, we have 4 times 1 minus 2, which is 4 minus 2, which is equal to 2. So just looking at these two answers on their own, notice that we have that the limit as x approaches 1 from all directions does not exist. So in order for a function to be continuous at x is equal to 1, the limit must exist, the function must exist, and they must be equal to each other. But 2 and does not exist are not equal to the same exact number. Therefore, we can say that f is not continuous at x is equal to 1, or you could say that f is discontinuous at x is equal to 1. Moreover, notice that we can see that the left-hand limit and the right-hand limit are not equal to each other. Therefore, you can also say that f has a jump discontinuity at x is equal to 1 by looking at the left and the right hand limits, so you can sort of have some graphical insight of what this function actually looks like. Let's look at another function to sort of see if we can see if it's continuous at some particular value. So example 2. Let's define g of x to be equal to x squared minus 5x plus 6 all divided by x minus 3 for x not equal to 3 because we can't divide by 0. And let's define it to be 5 when x does equal to 3. All right, so let's analyze the first piece first because obviously it has some issues. But if you analyze that function closely, notice x squared minus 5x plus 6 can be factored into x minus 3 times x minus 2 all over x minus 3. And notice that our x minus 3's will cancel and just leaving us with x minus 2, which is the graph of a line, but with a hole when x is equal to 3. So if we take a look at the first part of that function, x cannot be equal to 3, and the line practically looks like x minus 2. So it looks practically like something. In particular, it's going to look like something like this. Right, so that's what the first part of this function looks like. And in terms of our classification, this has a removable discontinuity, right? Because you can easily fill in that hole in order to remove it. So, does the value of 5 fill in that hole is the question that we're sort of going at here, right? So we clearly see that the limit as x approaches 3, because that's the point of interest. The first function's continuous everywhere except 3. The second function is continuous everywhere on the real line, and we can clearly see from this algebraic manipulation and also this picture that the limit as x approaches 3 of x squared minus 5x plus 6 divided by x minus 3 is equal to the limit as x approaches 3 of x minus 2, which is the same as 3 minus 2, which is equal to 1. And we see that g of 3 is equal to 5. So the limit exists and is equal to 1, and the function exists and it's equal to 5. So the question then becomes, are they equal? And the answer is no. Therefore, g is not continuous at x is equal to 3. In particular, because it has a removable discontinuity. So if we were to fill in our dot up there where that y value is equal to 5, that would be the graph of our function g for this example. For our next example, let's consider the sine function SGN of x. If you do not know this function, this may be also written in an equivalent way as the absolute value of x over x for x not equal to 0, because you again cannot divide by 0, and it's defined to be equal to 0 for x is equal to 0. You should be able to generate the graph of this function on your own. In particular, you will obtain a graph that is similar to the one shown on the right. X, y, and that is our function j, aka the sine function. So if you feed it a negative number, it will produce -1. If you feed it a positive number, it will reproduce 1. And if you feed it 0, it will return 0. So, is this function continuous everywhere? Well, obviously it's going to be continuous on x less than 0, it's going to be continuous on x greater than 0, but obviously at x is equal to 0, it does have some issues. In particular, the limit as x approaches 0 from the left-hand side of the sine function, we clearly see that that's equal to -1. And the limit as x approaches 0 from the right-hand side is equal to +1. And since these do not equal to each other, then we see that the limit as x approaches 0 from all possible directions for this function does not exist. Moreover, we can also see that the sine of 0 is equal to 0, and these answers must match and must both be numeric in order for that function to be continuous there. Therefore, we see that the function j of x, which is actually just the sine function, is not continuous at x is equal to 0. And if it's not continuous, you should be able to say what kind of discontinuity it has. We see that the left-hand limit and the right-hand limit are not equal to each other. Therefore, you can say that it has a jump discontinuity at x is equal to 0, but we clearly see that 0 is the only point in its domain where it has some issues. Now the next example that I want to explore is a little bit strange on its surface. In particular, the sine of 1 over x for x not equal to 0 and 0 for x is equal to 0. So if you try to sketch this out, it's going to have a very interesting shape. Notice that we're taking the sine of something. So this function definitely is going to be bounded in between -1 and 1. So that's obviously going to be the case. But as x gets closer and closer to 0, then the period is actually going to decrease and it's going to oscillate a lot more faster. So for example, we have a slow oscillatory behavior, and then it's going to sort of go chaotic as you get close to the origin and sort of calm down as you move farther and farther away. So the question becomes, what's going on in this area? And we're defining it to be equal to 0 at that origin. But do all of the points sort of approach that point as x gets close to 0? At least from this graph, it's hard to see because it's pretty much blurred, but that's precisely the point. So if we analyze this from the algebraic perspective, maybe we can see something here. So the limit as x approaches 0 of sine of 1 over x is equal to the sine of the limit as x approaches 0 of 1 over x. We know that the 1 over x function, sometimes called the reciprocal function, has this particular graph. We approach positive infinity from the right and minus infinity from the left, so therefore this is equal to, if we abuse notation, plus or minus infinity. But we know that the sine function, although it is periodic and well-behaved, does not get closer and closer to a uniform value. In particular, this limit does not exist. So since the limit does not exist and moreover does not equal to 0, therefore we have that this function k is discontinuous at x is equal to 0 because the limit does not exist. But now the fun question becomes, how do you classify this discontinuity? Some people will actually create a fourth category and call this an oscillating discontinuity because it's not really a jump, it's not really an infinite in regards to the original function, and it's not removable, at least for our intuitive eyes. But at least in this example, it actually does have one of those classifications because the issue isn't really sign. The issue is this 1 over x function. So as x gets close to 0, this has an infinite discontinuity, and that obviously is going to create some issues for this periodic function. Now, just because the interior of that function has an infinite limit, or in particular a plus or minus infinite limit, that does not necessarily the overall limit doesn't exist. Let me give you an example to sort of illustrate that. So let's consider example number 5. Let's consider the limit as x approaches 0 for e to the minus 1 over x squared. So if we define this function, for example, let's define f of x to be equal to e to the minus 1 over x squared for x not equal to 0, and let's define it to be equal to, I don't know, 1 for x is equal to 0. Is this function f continuous at that point? Actually, let's define it to be equal to 0 at 0. So if we plug in 0 here, what will we get? Well, negative 1 over x squared we know is going to have this type of shape. It's like a volcano upside down, or sort of like a vertex that water will sort of go down, right? So we see that this is going to be equal to e to the limit as x approaches 0 from both sides of negative 1 over x squared, which we can just abuse notation, at least for the time being, and say that's equal to e to the minus infinity, which is 1 over e to some arbitrarily large number, which we know is equal to 0. So in this case, we have that the limit is equal to 0, even though that limit is not necessarily finite, and the function value is defined to be equal to 0. Therefore, we see that as long as we define that point to be 0 at that point, that means f is continuous at x is equal to 0, but moreover it's continuous everywhere else because that function only has an issue at 0 and it's well behaved everywhere else, right? So we have that f is continuous on R and moreover at x is equal to 0. Sometimes we can have an arbitrary function that has some general shape, but we don't know the exact parameter values that we want that shape to have. Consider this 3-piecewise function defined by a line, a constant function, and a quadratic whose split point occurs at x is equal to 1, with parameters a and b. So obviously, until you decide what a and b are, you can't really determine whether this function is continuous or not, but it's possible that it be continuous for all values a and b, and that's pretty nice too. But for this particular example, it's possible that I choose my a and b such that the left-hand side doesn't equal to the function value, which is equal to 5. That much is obvious, right? Because f of 1 is equal to 5. And it's possible that I choose my constant values for b such that my parabola on the right-hand side doesn't line up with 5 on the right. So let's start with the easiest part in this problem, where the second parabola only has one parameter, because we know that the limit as x approaches 1 from the right-hand side of this function must be equal to the function value, and the left-hand limit also must be equal to 5 as well. But we only have one parameter in this third piece, so it's a little bit more easier to work with. So that's going to be the limit as x approaches 1 from the right of bx squared plus 3. Now we don't know b, but we can keep it as a free variable for the time being. So that's going to be equal to b times 1 squared plus 3, which is the same as b plus 3. And keep in mind, we need this to be equal to 5, and from this equation we can see that b must be equal to 2. So, with that being said, now we can move to the left-hand side. So the limit as x approaches 1 from the left-hand side is going to be equal to the limit as x approaches 1 from the left of ax, and we don't know a, but we do know b at this stage, so we can actually just replace that. So this is going to be equal to a times 1 plus 2, which is just the same thing as a plus 2. And again, the left-hand and the right-hand limits must be equal to each other, in particular equal to the function value, and both must be equal to 5. So when we set that equal to 5, we see that a must be equal to 3. So once we have that, then we can restate our function. So that means the function given by 3x plus 2 for x less than 1, 5 for x is equal to 1, and 2x squared plus 3 for x is bigger than 1 is continuous on the set of real numbers, and hence you can choose that domain and be confident that it indeed is continuous everywhere there. Now there is one other small thing that I do want to mention, and it's more so an argument on semantics. So let's assume that we have the basic function given to be this particular graph. In particular, f of x is equal to 1 over x, where the domain is equal to all real numbers except for 0. And let's assume that I don't want to define it at that point. So is f continuous? Is f continuous? So some people will say no, because it has a vertical asymptote at x is equal to 0. But keep in mind, x is equal to 0 is not part of its domain, right? And from the definition that we got, we say that function is discontinuous if the limit does not equal to the function value at that point. Here, the function value is not defined, which is some sense not the same as does not exist, right? There is some subtle differences between the two, right? For example, leaving it undefined and it not existing are a little bit different. So, is this function continuous? Some people will ask this sort of like a trick question. From the way we've defined it, the answer would be yes. But if we drop this assumption that 0 now is in the domain in some sense, for example, let's assume that it's equal to 0 for x is equal to 0. Let's assume that we sort of append that and call that our function. In this case, now we have that point there. Now it's not continuous at x is equal to 0 because it has infinite discontinuity or an extreme case of a jump discontinuity. So do pay attention to those concepts, and if some people ask, always refer to the definition that you're working with. So those are some of the basics associated to the continuity of single variable functions, and this is going to come in handy a little bit later. So I hope you enjoyed this video, and I'll see you in the next one. Take care.